Hey everyone, and welcome back to this class, Deep Reinforcement Learning in Python. In this lecture, we are going to look at the code for deep Q-learning in Theano. Since we already know the outline of this code, this lecture will focus on the details of this script. The relevant file for this lecture is dqn.theano.py. At the top, we're going to define some constants. First, we have max experiences and min experiences. Max experiences is the total size of our replay buffer, and min experiences is the size of the buffer when we commence training our neural network. Target update period is the number of training steps we're going to do between each time we copy the main network to the target network. IM size is the size of each frame when it gets input into the neural network. If you recall, the actual size of the frame is bigger and not square, but this is the way it was done in the original paper as well. Finally, K is the number of output nodes in our neural network, and also the number of possible actions. The breakout environment actually returns a bigger number than this, 6 in fact, even though the final two actions don't do anything. So it's simpler to set the number of actions manually to 4, which are the actions that are actually meaningful, instead of using env.actionspace.n. Next, we have a function to transform the game image into grayscale. Now you might wonder what's with these random numbers and why didn't we just take the average of the RGB channels to get the grayscale image? Well, these are the values used by programs like MATLAB and also TensorFlow. So if you want to check out the TensorFlow source code to confirm that that's the case, please do. Basically, it boils down to color science if you want to learn more. Next, we have a function called downsampleImage, which does multiple things. First, it crops the image, so this gives us a 160 by 160 box of the relevant parts of the screen. Next, we grayscale the image using the RGB to gray function, which we just described. Finally, we resize the image using imresize from SciPy. This converts the image into an 84 by 84 square. You can use 84, you can use 80. It shouldn't really matter too much. Next, we have the update state function. What this will do is take the current state and the new frame and return the next state. This involves throwing away the oldest frame and appending the newest frame at the end. Now you might think we don't need this because we have the replay buffer, but in fact this is useful because we still need to form a state in order to pass it into the neural network to get the Q values. Next, we define the replay memory class. Remember, the basic idea here is that we are going to pre-allocate all of the frames we plan on storing, and then we can sample states from the individual frames later on. The constructor is mostly for setting and initializing variables. So we take in the buffer size, the frame height, the frame width, the history length, which is the number of frames that make up one state, and the batch size for when we draw samples later on. After we save these inputs, we create some new attributes. First, we have count and current, which keeps track of the insertion point in our replay buffer. Next, we pre-allocate arrays to store the frames, actions, rewards, and done flags. Next, we pre-allocate more arrays, which is where we will store each batch we sample. Since each batch is the same size, we don't need to allocate new arrays every time we grab a batch. Next, we have the add experience function, which adds a frame along with the corresponding action, reward, and done flag. First, we check that the frame is the correct size and throw an error if it's not. Then we save the inputs into our array buffers. As you can see, we are now making use of self.current. As stated earlier, this keeps track of the current insertion index, which is circular. So once we reach the end, we start back at 0. This is why we update the value of self.current as self.current plus 1 mod self.size. Also, note that the self.count variable maxes out at the size of the replay buffer as well. Next, we have the getState function, which takes in an index representing the final frame in the state and returns the full state containing all the consecutive frames. First, we're going to check that the count is not 0 and that the index is at least 3, since that represents the final frame of the state, which has 4 frames. Then we index the frames array. As you can see, if you think of index as t, then it's t minus 3 up to t plus 1. Next, we have a function called getValidIndices. This is a helper function for sampling a batch, so it might seem a little strange that it doesn't return anything. Instead, what it's going to do is assign indices to be the indices corresponding to the samples in the batch and save them to an instance variable, self.indices. So here's where we check all those edge cases we talked about earlier. First, we sample a random index. It can be any integer from 4 up to the self.count variable. Now, we don't yet know if this is a good index, so we have to do some checks. First, we check the trivial case, where the index is less than the agent history length. This should technically not happen. Next, we check that the 4 consecutive frames don't cross the boundary of self.current. Because remember, self.current represents the pointer where we insert a new frame. Also remember that the replay buffer is circular, so you can imagine self.current being somewhere in the middle. After self.current represents the oldest frame, and before self.current represents the most recent frames. If we sample an index which is slightly ahead of self.current, but 4 frames behind is slightly behind self.current, then these 4 frames don't make up a valid state. The next case we have to check is that we're not at the boundary of an episode. So the same logic applies. If we imagine that we're somewhere in the middle of the replay buffer, and the index is slightly ahead of the done flag, but 4 frames behind is slightly behind the done flag, then we do not have a valid state. In all these cases, we just continue and select a new index. When we find an index that makes a valid state, we break out of the loop and assign it to the self.indices attribute. Next, we have the getMiniBatch function. The first thing we do is throw an error if the replay buffer is not full enough. Next, we call the helper function getValidIndices, which we just described. Next, we loop through all the indices we found and get the states for each index. Remember, we want the state S and the next state S prime for each index. So we assign these to self.states and self.newStates. Next, we return the batch. This includes the states S, actions A, rewards R, next states S prime, and done flags. Next, we have a function called initFilter. This will be used for the convolution layers to get the initial values of the weights. As usual, we want the weights to have variance 2 divided by its input size. Next, we have a function that computes the atom updates given a cost node and a list of model parameters. I won't discuss this too in depth since we've already done so, but feel free to ask about it on the Q&A if you don't understand what you're seeing here. Next, we have the convLayer class. In the constructor, we initialize the weights and bias and make them into Theano shareds. We also keep instance variables for the stride, params, and activation function for later use. In the forward function, we perform the forward operation, which is to pass the input through a convolution using our weights, and then add the bias and pass it through the activation function. Next, we have the hidden layer class, which follows essentially the same pattern. In the constructor, we initialize the weights and bias and save them as instance variables. In the forward function, we perform the forward operation of a neural network layer. Next, we have the DQN class. The constructor does a majority of the work, so this is the function you want to pay attention to. As input, we take in the number of outputs k, the conv layer sizes, and the hidden layer sizes. First, we assign k to an instance variable. Then we create Theano variables for the inputs and targets. The input is x, which is a 4-dimensional tensor. The targets are g, which is a vector of predicted returns. And we also need the actions, which chooses which output node should be used for the prediction. This is also a 1D array, but of integers instead of floats. Next, we create the convolution layers. In each iteration of the loop, we're passing in tuples of the number of output filters, the filter size, and the stride. Note how we're doing some extra work here to calculate the size of the image after each convolution. This isn't necessary, but it's a helpful sanity check. The next thing we do is get the output size directly. This is a much more explicit way of getting the output size and is preferred since convolutions in different libraries are not exactly equivalent. For example, the same code in Theano and TensorFlow would yield different size outputs. So checking the size explicitly is the most surefire way of getting it right. To do this, we create a Theano function that just outputs the last output of forward functions from the convolution layers. Then we can pass in a dummy input and check the size of the output. This will tell us the input size of the first fully connected layer. So you can see I've saved that to a variable called flattened output size. Next, we pass the data through fully connected layers. These are specified by just a single number, the hidden layer size m. Finally, we pass the data through a final fully connected layer to get k outputs. Next, we're going to collect all the model parameters into one list. This is required for two reasons. First, we'll need a list of all the model parameters when we copy one neural network to another. The second reason is we'll need to pass these into the atom function to get our updates. Next, we can pass in the output of the convolution into our final fully connected layers. This gives us y hat, the output prediction. Once we have that, we can build up our cost. To build the cost, we have to choose only the y hats, which correspond to the chosen actions. Luckily, in Theano this is easy because we can index tensors just like NumPy arrays. This is not possible in libraries such as TensorFlow, at least not yet. Next, we calculate our cost variable, which is the mean squared error between g and the selected action values. Next, we can pass in this cost variable and our parameters into the atom function to get our model updates. Using this updates list, we can compile a Theano function for the train op. It takes in the inputs, the targets, and the actions and performs the updates. Next, we can compile the predict op, which takes in the inputs and outputs the predictions. So that's all for the constructor. Now we have a couple more functions for the DQN class, but they are all much smaller than the one we just looked at. The next function we have is the copy from function. This takes in another deep Q network and copies its weights to itself. In Theano, this is easy because we collected all the model parameters in an attribute called params. So all we need to do is loop through the params of both networks in corresponding order and use the getValue and setValue functions to copy each parameter. Next, we have the predict function, which runs the predict op on a given state. This should return the Q values over all actions. Next, we have the update function, which runs one iteration of the train op and also returns the cost. Note that it takes in the states, actions, and targets, which correspond to the placeholders we created earlier. Finally, we have the sample action function, which uses epsilon greedy to select an action. It takes in two arguments, x, which is the state, and epsilon, which is the probability of doing a randomly selected action. As you can see, this makes use of the predict function we wrote earlier. By taking the argmax, we get the action, which yields the largest Q value. Next, we have the learn function. It's nice to encapsulate this into a function because setting up the update is non-trivial. We have to take a batch of data from the replay memory, calculate the targets using the target network, and then pass those targets into the main network. So the first thing we do is use our replay buffer to grab a randomly sampled batch of data by calling getMiniBatch. Next, we want to calculate the targets. First, we calculate the Q values for the next state, the S primes. Then we select the maximum Q values for each state over all actions. Finally, we discount the Q values using gamma, multiply by the inverted done flags, and then add the reward. The most confusing part of this is why we invert the done flag, so let's explain that in detail. As you know, the value of a terminal state is 0. And also, booleans are treated as 1 and 0, so true equals 1 and false equals 0. Therefore, if done equals true, then done equals 1, and inverting that gives us 0. Multiplying by 0 gives us 0, which is what we want the value of a terminal state to be. If done is false, then inverting it gives us 1, which gives us the usual TD target. Finally, we call the update function we defined earlier and return the loss. Note that the loss is not particularly interesting in this case, but rather the rewards over time. So we most likely won't look at it, although you could plot it if you want. Next, we have the play1 function, which goes through one episode of the game. As input, it takes in the environment, which is the environment object, total t, which is the total number of steps played so far, experience replay buffer, which is a replay memory object, model, which is the main neural network, target model, which is the target network, gamma, which is the discount factor, batch size, which is the number of samples to draw for each training iteration, epsilon, which is the current value of epsilon, epsilon change, which is the amount to decrease epsilon on each step, and epsilon min, which is the smallest epsilon we want to reach. So this looks complicated, but really, this function is just looping through each step of the episode until it hits the done flag. To start, we record the current time and assign that to t0. Next, we reset the environment, get the first observation, transform the observation, and then stack the observation 4 times to get the first state. Next, we create some variables for things we want to keep track of. Total time training will keep track of the total time we spend training our neural network. Num steps in episode will keep track of the number of steps of this episode. Episode reward will keep track of the sum of all the rewards. Next, we enter a loop that exits when we see the done flag. Inside the loop, we check if it's time to update our target network. If it is, we call targetModel.copyFrom and pass in the main network. Next, we sample an action from our model using the sample action function. Next, we perform this action in the environment. We get back the next observation, the reward, and the done flag. Next, we transform this observation, meaning we downsample it and convert it to grayscale. Next, we use the update state function to create the next state. Next, we update the episode reward variable with the reward we just got. Next, we add the observation, action, reward, and done variable to the experience replay buffer. Next, we run one iteration of training on the main network. Notice how we wrap this in datetime calls, so we can keep track of how long we spend in the learn function. The duration is assigned to the variable dt. Next, we add the number of seconds in dt to our total training time. We also add 1 to the number of steps in the episode. Next, we assign the variable nextState to the variable state, since on the next iteration of this loop, it will be the current state. We also add 1 to total t, which is the total number of steps we've done so far. Finally, we update epsilon by subtracting epsilon change from epsilon, but we don't let it go below epsilon min. Lastly, we exit the function and return some of the information we collected. Next, we have the smooth function. This is just a simple function that lets us keep track of the average return over the last 100 episodes. This is useful because the actual returns will vary by a lot, so this gives us a more stable looking plot of the return over time. Finally, we have the main section. First, we define our neural network parameters. As you recall, the variable conv layer sizes contains tuples of the number of filters, the kernel size, and the stride. The variable hidden layer sizes contains the size of each hidden layer that follows the convolutional layers. Next, we have gamma, the discount factor, batch size, the number of episodes to train on, and we initialize total t to 0. We also create our replay memory object and pre-allocate the episode rewards. Next, we define our epsilon variables. The initial epsilon is 1, so we always explore, and the final epsilon is 0.1. We would like to transition from 1 to 0.1 over 500,000 steps, so we divide 1 minus 0.1 by 500,000. Next, we create our environment object, our main network, and our target network. Next, we populate the experience replay buffer with episodes played using completely random actions. So we loop through min experiences, and on each step, we choose a random action and perform the action. We collect the next frame, the reward, and the done variable. We transform the frame and then add this information to the replay buffer. Note that there's no need to see the actual states here, because the actions are chosen randomly and don't depend on the state. If we hit the done flag, then we just reset the environment and start again. Next, now that our replay buffer is full, we can start playing real episodes and training our network. Luckily, all the work has been done, so we just call the play1 function. This gives us the episode reward, which we store in our array of rewards, and some other useful information which we print out. When the loop is done, we print the total duration, and we plot the total return per episode. So that's everything for this file. Let's run this and see what we get. Alright, so it looks like we do pretty well. As you can see, the model ends up learning how to play the game proficiently.